Everybody, it's my great pleasure to introduce the USC Center for AI in Society's seminar speaker today. It's my colleague Swabha Swayamdipta. I hope I did it justice. Swabha is a Gabilan Assistant Professor of Computer Science here at the University of Southern California. And we are really happy to have her join our department and join the Center for AI in Society. She works at the intersection between natural language processing and machine learning. In particular, she focuses on estimating bias and data set quality estimation, as well as semi-automatic data collection. So I'm really excited about the talk that she's going to give us today. Thank you, Swabha.
Thanks, Petra, for the introduction, and thanks everyone for coming to my talk. I will be talking about contextualizing bias in hate speech detection through annotator perspectives. And before I start, I would like to give a fair warning. Some of the content might be offensive to the audience, especially the examples that I share. All right, so with that, I just wanted to share a few icons to start with. And if you're like me, at least one of these icons sets something deep in you, this deep urge to look at your phone. And at the same time, the same icon has at some point set off something unpleasant in you, has exhausted you in some way. So this is not a unique experience that you might have had. The reason this happens is because anybody who has spent time on social media has also seen the incidence of a ton of undesirable, offensive, and sometimes even hateful content on these media platforms. And this content is what my talk today focuses on. To be specific, hate speech refers to disrespectful comments, including but not limited to identity attacks, such as slurs, derogatory content, profanity and vulgarity, and threats. So these are things that I hope none of you have come across, but they're very, very, very common on social media platforms. So these attacks or the hate speech may or may not be explicit or intentional. So an example of something that is subtle and yet hate speech unconsciously expresses a prejudiced attitude. So for example, the question, "But where are you really from?" is a microaggression, which may make the listener feel unwelcome. So in this talk, I will use the terms hate speech and toxic language interchangeably. However, finer distinctions can be made on these terminologies. All right, so in the current news cycle, hate speech has acquired an even more urgent meaning to some, myself included, given what is happening in social media. I've convinced myself that Twitter is a media platform that I need to use as an academic, but some of the recent events have been troubling. And so the problem of hate speech is something that is very, very recent, very, very urgent, and something we really need to deal with. So what are some possible solutions? Now, due to the sheer volume of content on social media platforms, the dominant solution is to use automated methods for hate speech detection. So this is usually seen as a binary or an NeurIPS classification task. So given a post, we train a classifier to predict whether or not it has some toxic content. So one primary example of an API that provides this hate speech detection is the Perspective API, which was created in collaboration with folks from Google, as well as Jigsaw. So we will be using Perspective API throughout as a running example of a tool that provides us hate speech decisions. And so this task of hate speech detection has indeed blown up in the current years. There have been a ton of research papers as well as platforms that have come out to handle this task, which has been terrific to see. However, if we look at the progress that we have made so far on hate speech detection, with the particular examples of, say, this Perspective API, let's see how this API does. So here are two tweets. I identify as a Black gay woman, and I identify as a straight white man. The first tweet gets a very high toxicity score, whereas the second one gets a very low toxicity score. Almost, it's considered safe on this platform. I don't have the exact dates when we queried this API, but these are results from this Perspective API. They have since corrected some of these judgments, but this is something we saw. Similarly, if you have a tweet that has some kind of vulgarity or profanity, it may or may not indicate some kind of hateful intent, such as the first tweet here, which uses the F word, has been used for indicating a lot of emotion. However, it is seen as toxic in some of these platforms, whereas something that does not use any profanity, but still might be, spreading some hateful ideas is seen as safe. And finally, tweets which are in dialects that are not primarily what is called as the standard American English dialect, and especially tweets which are in African American English dialects are seen as toxic content, even though the context in which they occur might make them non-toxic. These might contain reclaimed slurs, such as the first tweet here, if it has come from an African-American English speaker. However, it is seen as much more toxic than the second tweet. So this kind of indicates that there are lots of existing biases, biases in these hate speech detection tools, and this has become an issue, and this is the particular issue I'm interested in addressing. So the question is, to what extent are these biases simply a machine learning problem that needs to be solved? Are there training objectives that we can use to solve this problem of this kind of bias in hate speech detection classifiers? And this is exactly the question that we tried to ask in our work that came out at EACL last year. So if it is a machine learning problem, it is very likely that either it can be addressed by looking at the data or by looking at the model. And so the goal here is to reduce to as much extent as possible the presence of this bias in our models. So the first approach that we look at is how we can clean up the data set on which our models were trained to reduce the bias. On the other hand, we could also fix up a trained model. We could additionally train it on different objectives or do something during training such that it avoids picking up these biases. So let's look at cleaning up the data sets. For this task of cleaning up the data sets, we looked at two different methods. These are data filtering approaches. The first involves an adversarial filtering of data set biases. This uses an algorithm which looks at an ensemble of linear classifiers and looks at the decisions that the linear classifiers are able to make correctly. The assumption here is that if linear classifiers, which are much more simpler than neural classifiers, are able to detect something very easily, those examples may contain some of these lexical biases. So this is an algorithm that came out from myself and collaborators at ICML a couple of years ago, and we will be using this for cleaning up the data sets. The second method we'll be looking at is data maps, which is also a method that came out of myself as well as other collaborators. And we'll go into a little more detail on this specific method because it is important for later on. One key thing here is that neither of these data filtering methods assumes any predefined notion of bias. It doesn't assume that the bias is concentrated in certain lexical items or it is directed towards certain dialects. We're just going to look at the performance of these models on the data set and using certain assumptions, figure out what is the bias data. All right, so what are these assumptions for the adversarial filtering case? The assumption is that of the linear classifier getting the examples predicted correctly. For the data maps case, this is what a data map looks like for a data set that deals with a natural language understanding problem. This is not hate speech detection, but as you can see, this is each point on this data map indicates a single instance in the data set, which has been trained using a Roberta model, which is a fancy feed-forward or transformer-based model, if that is familiar to you. That's not, the model itself is not important as long as we know that the data set has been used to train any given model. So here in the data map, we have these different regions in the data set. On the top left corner, we have examples which we think are easy to learn with respect to the model because the model predicts these instances correctly throughout the course of training. On the bottom left corner, we have instances which are hard to learn, which the model has predicted incorrectly throughout the course of training. And on the right-hand side, we have ambiguous instances, which the model kept changing its decision on throughout the course of training. And so these are the regions within the data set with respect to this model. And you can look at the details in the cartography paper per se, but a couple of things I want to outline to figure out like how we can filter the data to eliminate bias is that most of the data is focused in that easy to learn region. That's a very dense region, especially when the model is very capable of learning the data set. And we also think that most of the biases in the data might belong to that region because the model is able to predict those instances very correctly. So the assumption for this filtering approach is that the bias in the data set might belong to that region. So for filtering, we ignore the easy to learn region and we consider subsets which are focused in the ambiguous region or the hard to learn region of the data map. Any questions? This might be a lot. Yeah, so hate speech, yes, so the question is, it's unclear why the easy to learn region corresponds to biases for hate speech. So the understanding is that the biases come from adherence to simple lexical items. And the minute the model sees, say, the F word, it thinks it is hateful content, even though that might not be true. It might be showing something like emotion. And because these are, the model relies on these lexical cues to come up with this decision, it is very easy for the model to do it right from the first step of training. And therefore, we assume, and we'll see that this is indeed the case, that the easy to learn examples contain these biases.
Mm-hmm. Can you comment on what is the typical labeling look like in these applications, and what is the agreement among different labelers there are multiple?
Yeah, we'll actually come back to that question, but for the purposes of this part of the talk, it is just a binary classification task, hateful, not hateful. we're operating under that assumption. I'll talk about agreement, etc. later on. All right. So this is a data-centric filtering approach to reduce biases. Now looking at the model, how can you fix up the model so the model biases go away? We adopt this architecture from Chris Clark and his group at the Allen Institute of AI. It's called L-Mixin. So it might look like a very complex model, but what it's doing is it is an ensemble of two different models. One is a bias-only model, which only uses bias features to be trained. And then there is a regular model, which uses all possible features. This ensemble is what the full architecture is trained on, but at inference time, you discard the bias-only part of the model and you make inferences with the full model. So the hope is that this is a cartoon representation of this model. So you have this bias-only model and the full model. And the hope is that during training, the bias-only model will pick up on all the features which have these biases, and the full model will be able to focus on the other features. And during inference or prediction, we only use the full model, which will hopefully not give a high weight to the bias features. So we will be using this approach as a debiasing step. So one key thing you might have noticed is that this assumes a predefined notion of bias. So you need to define something as these bias features. So to do that, let's go back to the examples we saw before. The first couple of examples is an example of an identity bias. Here, Black gay woman, a straight white man is an example of an identity. These may or may not be offensive identities, and we'll look at that a little more closely later on. So these are lexical features because given some text, you can figure out what part of the text refers to that identity. The second kind of bias is swear word bias. So, we have a list of profanities that we could consider for detecting whether or not an example has this kind of lexical bias. Just because of the presence of the profanity, if the model classifies it as toxic, then it contains the swear word bias. And the third example is that of dialectal bias. So because of the presence of African-American English markers in the first post in the last couple of examples, the model can predict this as toxic content. So to determine what these swear words and identities are, we use keyword matching using existing lists. And for the second one, we use a classifier based on prior work, which identifies what text has how much likelihood to be in a particular dialect of English, either African-American English or what we call white aligned English, which is anything but African-American English. All right, so these are the three kinds of biases that we will use for model-based debiasing. All right, so maybe a question you have here is for data filtering, why not simply rely on these lexical cues to clean up the data? Maybe we just remove all the instances that have the F word. And that should do some kind of data set filtering. But this is not always applicable because in these two examples, the first example uses the same profanity as the second example, but the first example most likely expresses an emotion and it's not intended to hurt, whereas the second one clearly is intended to be hurtful. So over-relying on these lexical cues for data set filtering can be misleading. All right, so we saw a couple of, the overview of a couple of debiasing methods. One is data-based, one is model-based. So the question is, are these current NLP debiasing approaches effective for debiasing toxic language detection? The title of the paper is kind of a spoiler alert. So there are significant challenges that we face in automated debiasing for toxic language detection. All right. So to see how effective the methods that we saw so far are for debiasing, we can categorize the inputs for evaluation. So we'll consider different categories of the data and compute our evaluation metrics on those slices of data. So the first one, and these are different examples of the lexical biases. So the first one contains items which or contains posts which may or may not, which may contain possibly offensive minority identity mentions. We call this OI. The second category contains possibly offensive non-identity mentions, such as slurs, swear words, or other kinds of vulgarity. And the third one contains non-offensive minority identity mentions. So this particular category should ideally not be associated with any notion of toxicity. However, that distinction is not always clear. Sometimes, such as in this tweet, just mentioning the word Muslim should not make it something offensive, but the context in which this is used can make it offensive. So these are called three different toxicity triggers. So OI, NOI, and ONI are the three toxicity triggers. The first metric we will be using is Pearson's correlation between the gold standard toxicity label and whether or not it contains different identity mentions. So this metric will be used for looking at how effective our dataset-based filtering is. The second metric is we will be looking at the false positive rate on tweets that belong to these three different classes. So we don't want tweets that belong to these classes to be simply, be predicted as toxic. We want them to be predicted as toxic when toxicity actually exists. And we will also be looking at overall F1 scores. All right, so how does data filtration do for lexical biases? So again, here we will be considering the original data set trained with the original model. Here we are again using a transformer or a feed-forward net, neural net-based architecture for all these experiments. And the second block of methods uses different kinds of data filtration techniques. So the first one is random. The second one is the AFLIGHT, the adversarial filtering algorithm I mentioned. And the remaining three are filters based on different regions of the data map. So this is what the original model does on this correlation metric. So here we are just looking at data correlations between examples that contain these different identity mentions and the presence of toxicity. When we use random, it shouldn't affect the random filtration. It shouldn't affect the presence or absence of toxicity too much. And that's indeed the case. For the next three methods, we see that the overall associations go down by a little bit. And especially this is true when we use a model that is trained only on the hard subset of the data. So that's shown in green with the black border. However, if we were to train just on the easy subset of the data where I hypothesized we might have lexical biases, and there was a question about that, we see that the associations go up. So the easy portion of the data actually contains more posts that have these identity mentions, which are associated with a toxic label or a hate speech label. So this shows that the hypothesis we originally had is actually born in data. So hard subsets contain the lowest amount of lexical biases. Again, this is just a data question. We haven't trained any models, but what we see, we'll see later on is how do models do when they're trained on these subsets of data.
Sorry,
yes.
You're showing the R-square is the correlation between what and what in the data?
So the presence of, for each of these R's, it is the presence of one of these identity mentions and the presence of toxicity, the correlation between that. All right, so how do these different models do? Here, I have marked the things that you see with a gray border are the model-based techniques, and the others are the data set filtering techniques. So for AFLIGHT and data maps hard, the model has been trained on just 30% of the data. Whereas the L-Mixin model, which is the model-based debiasing, has been trained on the entire data, but it uses this bias-only model that is trained to figure out the toxic tweets. Yes, Robin.
Actually, I had a question on the previous slide, actually.
Yeah.
So I was wondering, like, is there a way to just like explicitly filter the data to make all the correlations zero? Like you just like downsample the thing that's overrepresented.
Yeah, but remember the example I showed with the emotion and F word? It is possible that you totally remove all the presences of certain identities. So maybe you'll remove all the examples that talk about being Muslim, but
yeah,
that's.
Well, yeah, I don't want to remove all the examples about being Muslim. I just want to balance the examples that are Muslim to be like the same rate of toxicity as the examples for every other.
Right, you could do something like that. Possibly. We wanted to be a little more bias agnostic because sometimes we don't know what triggers a certain kind of bias. And I'm blanking out on an example of that. There was like an age-related bias that we did not see previously. There was some bias against older folks. And that's not something we typically considered. And that's something that we actually saw with the data filtration. So it's hard to enumerate all different kinds of biases beforehand. But you could absolutely do some clever data balancing. Yeah.
But you're saying that access to the ground truth without access to the ground.
You need access to the ground truth to do this. Yes. Yeah. Which, I mean, to be fair, all these methods, data filtration methods also have. So, yeah. All right. So, so as you can see, all these methods are only able to reduce the false positive rate for each of these three categories by a little bit, if at all. So AFLIGHT, for instance, does not affect, and in some cases increases the amount of lexical biases as given by this false positive rate. And the data maps hard method is only reducing the first category of lexical biases, but not the other. So one big takeaway here is that this reduced associations in the data from filtering the data might not lead to debiased models. That is, only training on the filtered data may or may not lead to debiased models. Then there is this other finding we had when we looked at just the F1 measure for the entire data set. For this L-Mixin method, which was doing a little better than the other methods. And you see that the overall accuracy or the overall F1 for the positive class is going down. So even though it is removing some bias as given by these false positive rate metric on these different categories, it is also reducing the overall performance. So there is no one metric so far that we have seen that does really well across the board.
Essentially means that they've also reduced they've increased the false negative rate.
Exactly.
Right? So,
yeah, exactly. So that doesn't quite work. When it comes to dialectal or racial biases, we see something of a similar effect here. Here now, the data set filtering metrics seem to be doing a little better. We actually also tried a different out-of-distribution test set, which contains a self-reported race and ethnicity. Remember, for detecting African-American English, we are using a classifier to tell us whether or not the tweet is in African-American English. But here the tweets are there, are provided with the self-reported race. But even in that test set, you see like the method that was doing the best, which was data maps hard, that actually increases the amount of dialectal biases in this out-of-distribution test set. So there is no filtering method that works across data sets and across these different biases. So even though you can see that the bias has been reduced partially, it doesn't hold over generalized to different settings. All right, so this was obviously very disappointing. We thought like we are coming in as machine learning people, we know what we are doing, and we would fix this problem. And it turned out to be very hard. So we started looking at what might be going on. So we looked at the data, and these are some examples of tweets with their gold standard annotations. So as you can see, the skull means toxic, and the leaves mean safe. I'll give you a second to read these tweets. How many here agree with all the labels? Yeah, so it turns out that if you take a model that was trained on the easy to learn subset of the data, the model predictions agrees with all these three labels. So what's happening is that this model is actually, as we knew, it was capturing these biases. And perhaps there are certain biases that are not like immediately evident to us that the model captures and gets these predictions correctly. But the hard to learn or the model that was trained on this hard to learn subset of the data, which might actually be doing the right thing, gets these answers wrong. So the big takeaway here is that the annotations themselves are not super reliable. There are some annotation errors, and there are some ambiguous examples, which might be completely skewing up what we think is the performance of these debiasing approaches. So maybe we see improvement in terms of false positive rate or reduced associations, but that doesn't quite mean that we're doing the right job. So we decided that perhaps it is worth looking at the annotations themselves, and to the guiding principle here was work that had come out a couple of years ago by one of my co-authors, Martin Sapp, where he showed that when you are collecting annotations for hate speech detection, sometimes just priming the annotators by telling that, hey, something might appear offensive, but might not be so, because maybe it uses some reclaimed slurs like the N-word. This really benefits the quality of annotations we get. Mind you, these are still just binary annotations, but the crowd workers seem to benefit a lot from what they called it dialectal priming. Just telling them like, hey, this may not be as toxic as it might seem at first. So inspired by this direction, we decided that let's see what will happen if these so-called toxic tweets, which are in African-American English, were to preserve the content, but did not contain the AE dialect. So to do this, we did something that is not widely recommended at a large scale, but we wanted to try it out as a pilot. So we used GPT-3 to do a few shot translation of the tweet in AAE to white-aligned English. And we got reasonable results. So these are the 3 white American English translations. And then we obtained a silver standard label using an existing classifier to get the tweets. So first of all, this already shows the model bias just because it drops certain words, but doesn't change the semantics. Now the model thinks this is something that is not toxic, even though the original tweet was arguably non-toxic as well. And then once we collect this new data set with the translations, we will train a new model. And so we relabel the AE tweet as non-toxic. So we don't actually use the translated post, but we use the original post, but with the flipped label if the white American English counterpart is predicted as non-toxic. So this resulted in about 12% of the toxic AE tweets being relabeled. And we did like a small scale manual analysis of how well this, this translator was doing. And we were satisfied with 80% or so of the results. So we decided to go with this. But again, this is synthetic data, and I will urge a lot of caution against using this method, because at the end of the day, this is data that is based on real users' tweets, and we should not be replacing that with something GPT-3 generated. But we wanted to show this pilot as an example of what might be happening if annotators used their preconceived notions of what is toxicity to come up with the labels. So this is the result of the pilot study. So in addition to the methods that we already had, we now can look at what happens when you relabel the data. And looks like the relabeling process actually improves performance when you just train a model on that relabeled data. So you don't need to do any additional filtering or model debiasing. It just works on relabeling. So looks like relabeling is probably more promising than the current debiasing methods, especially for this task where the data set contains lots of annotation errors, ambiguity, and so on. All right, so to summarize real quick, we see that once bias exists in these data sets and models, it is very hard to remove. Secondly, data relabeling can be more promising than some of these debiasing approaches. So this direction of research brought up this big question. This was something of an existential question for us back then. Is automatic debiasing for hate speech just a non-starter? But to really answer this in a nuanced way, or to do better on this debiasing task, there is really another question that we need to answer, which is what is the cause of these biases in the data in the very first place? Where are these biases coming from? So this is what we try to answer in follow-up work with all the original authors, and Laura, who is a social psychologist at the University of Washington, who had lots of intuitions about this task of hate speech detection. All right, so again, going back to the task, this is how the task is annotated. We take a tweet. This is given to crowd workers. Perhaps we get a variety of different labels. And these are, for simplicity, we are only considering 0-1 labels here. And even then, even though we might get different opinions, the way we train classifiers is we take the majority vote among all these decisions, and then we train a classifier that predicts this. So hopefully this answers your question a little bit. And the annotator agreement, depending on what data set you look at, is very different. And usually these tasks have lower annotator agreement. because of the subjectivity. But then again, if it is collected in a very, if it is not carefully collected, you may see an artificially inflated annotator agreement in these tasks. So as a result, you'll see, again, the same kind of biases. So the first one is an example of an AE, dialect-based bias. And the second one, the one that is predicted as safe by the model, is something that is actually anti-Black, but is predicted as safe. And the last one is something that contains a vulgarity, but is still predicted as toxic, even though it is just expressing emotions. All right, so even though the users on these platforms might be very diverse, the annotators that we select are only a fraction of those users. So they are relatively homogeneous, but the users may or may not be as homogeneous a pool. And we know this because of the study that we did, which I'll get into. Unfortunately, though, the model learns the opinions of this small minority of users within the entire pool of users that use social media. And the second thing here is that majority voting might actually smooth out the ambiguity. Here, we still have two annotators who are predicting something as toxic, even though everyone else thinks it's safe. But once you do a majority, you will label that as a safe post. All right, so the question that we are interested in is to understand the what, who, and why of toxicity annotations. What refers to the different text categories that may trigger a toxic label from annotators. The who refers to the demographics of the annotators themselves, race, political leaning, and gender. However, demographics should not be everything. There might be multiple people who have the exact same demographics, but have different attitudes towards different topics. And that's what we try to capture as this why question. What are the different annotator attitudes and beliefs that lead them to consider something as toxic? And this is where the social psychologist we teamed up with really brought in her expertise. And just so we are all on the same page, this is based on a US-centric sociocultural perspective, and things might change a lot depending on where you are. All right, so the text categories we consider, again, very quickly, are African-American English, anti-Black content, and vulgar or profane language. But we consider these text categories in a mutually exclusive way. So we don't consider tweets that are both in AE and contain vulgarity, for example. So we can consider mutually exclusive categories this time. But we look at a very small set of tweets or posts. So only 15 posts per category, and these have been manually selected by us and then vetted more carefully by other students that we hired for annotating this task. All right, the two questions we asked them is how racist is a post and how offensive is a post to you and to anyone else. And we collected their answers on a 5-point Likert scale. For the who question, which is the annotator demographics, we selected an annotator pool on Amazon Mechanical Turk, specifically asking them if they are comfortable to declare their identity by gender, by political leaning, by race. As you can see, we still didn't get perfect parity across different demographic categories. It is insanely hard to hire annotators who are not women, who are conservative, and who are Black. So this is the best we could do after several weeks of trying to hire annotators. However, this is much better than what you would do as like if you spent no effort into looking at the demographics, you would do much worse. So that again says that the annotators are a homogeneous pool. So for why, we looked at different annotator attitudes and beliefs. I won't go into the details of each in the interest of time, but there are a couple of important ones. First is the endorsement of racist beliefs. This is based on a scale called the Modern Racism Scale from McConaughey. And this has been proposed in social psychology literature and used very widely since it came out in '86. So it has been around for a long time. And we used just their scale, which consists of a bunch of questions, and you would answer these questions, which will give you some kind of a score to rate you as where you lie on this racist belief scale. All right, so let's look at some of the results. So these are in terms of correlations. So for the anti-Black posts, we found that the annotators who are conservative men and white find anti-Black posts safe or non-toxic. And when we look at the attitudes that correspond highly is if they rate highly on the scale of endorsing racist beliefs, or they score highly on endorsing free speech. On the other hand, anti-Black posts are seen as more toxic by by annotators who are liberal, annotators who are women, and annotators who are Black, and with the attitudes where they rate highly on perceiving the harms of hate speech. These are all very intuitive and very consistent with findings that have been seen in prior work. And I would encourage you to check out those other works that have studied these questions in much more detail. We see similar trends for African-American English posts. These are seen as more toxic by annotators who are conservative and annotators who rate high, again, on endorsing racist beliefs. All other correlations were non-significant. And finally, for vulgar and profane language, we see that annotators who are conservative and those who rate highly on linguistic purism, that is, they consider that English should be spoken in a right way, there is a right way to speak English, those folks find vulgar and profane language more toxic. And also annotators who were high on the traditionalism scale also found this more toxic. So at this point, you might be thinking, okay, fine, this is great. Every post got 641 different annotations, but this is like a very small set and they're mutually exclusive. So you can say that they are somewhat atypical. When things are hateful, they might contain these different attributes. So we wanted to see if these findings generalize. So we looked at a larger pool of data, which had more overlapping categories, but each tweet now received only 120 annotations. And we looked at a total of 570 posts. And we saw that most of these correlations hold, except for one, which is the vulgarity and who finds vulgar language more toxic. Other than that, everything had pretty high correlations, which kind of says that these findings generalize to larger settings. And again, this is all on the data side of things, what happens when it is models. So again, we looked at Perspective API, and without describing the results too much, the main takeaways we saw was that Perspective API rates more like annotators who are high in endorsing racist beliefs, especially for anti-Black content. For African-American English, Perspective API rates like white annotators and or women annotators, which is very interesting because you would think that Perspective API, which actually does a good job in employing like a diverse pool of annotators, still falls into these simple categories of specific demographics. So models in general might reflect specific annotator identities and beliefs. All right, so to summarize the key findings that I have shown so far, toxicity detection models and data sets exhibit social biases. Once created, these biases cannot be very easily removed, either in the data or in the model. And toxicity detection models end up reenacting specific ideologies of different people, even though it is meant for users from many different demographics with many different beliefs. All right, so what can we do better? We could collect annotator beliefs and attitudes as we are collecting the annotations, and we could also make it more than just a task that you have to do as a human being. You probably need to contextualize your annotations in what your demographics are, what your beliefs are, and so on. We might benefit from contextualizing toxicity prediction in social variables. So something may or may not be toxic in isolation, but when you consider it in the context of a conversation that is actually happening, or some kind of a setting where the speaker and listener are in a power differential, something may have a different meaning, may be more toxic. And this is research that we are currently pursuing. And the final thing that we could do is reimagine hate speech detection as more than a simple classification task. And this goes beyond like moving from a binary to an n-ary classification, but maybe this is something that needs to consider the uncertainty of the model as well. Maybe instead of just predicting a single probability of something being toxic and non-toxic, perhaps doing something more nuanced, where the model is able to predict, like, if your beliefs are so and so, there is a bigger likelihood that you find something more offensive, and so on. And this is an exciting direction of future research that I'm very excited about. So that's all I had for you today. This is my lab that I'm just starting since August. If you're interested in learning more about what we do, please let me know. Thank you. And take questions.
Any questions from the audience? So well, I guess my question is, what should Twitter do? I guess in the perfect world, you would have a model that would say here, one point from each of those 8 scales and predict whether it's toxic. But like Twitter would have to, for example, decide I'm gonna block out everything that everyone considers toxic, or everything that if you have at least one person considers toxic. Like, how do they use this kind of technology?
Yeah. Okay. So the question is, what should Twitter do? And you'll have to ask Elon Musk about this. But the follow-up question was that, like, should you consider these, these scales that we had for attitudes and beliefs, and should you just label something as toxic if one annotator or one person found it toxic as opposed to multiple people? So it's definitely like a very valid question, and the whole point of this entire area of research is that we cannot have like these simple 0-1 decisions, because it is a very subjective topic. My opinion may not agree with yours, and both our opinions could have then further nuances. Like, maybe we agree on surface, but if we dig a little deeper, that might be very different. So there are a bunch of strategies that need to be used. Perhaps a good use case that we could try to implement is before the annotator pushes the send button, maybe Twitter pops up a message saying, hey, are you sure about this? This might be considered by some people as offensive. Do you still want to post it? And this is something Twitter is already doing when you share links etc. And something of this nature could be implemented. And then again, we could have much more, sophisticated methods that look at a history of things that we say, and maybe people who have a history of never posting anything toxic are using the F word suddenly, or even something that's considered a much worse profanity. Like maybe they're saying it because they're very angry or they have a lot of emotion about some topic. So it could give you like a nuanced understanding. Like you could build these systems that talk to the users before they send out content. I think that to me seems like an actionable solution for now, but there is no one solution that will work in every case.
So in the later part of the talk, you mentioned it seems that what is toxicity is sort of subjective, and as you have this data, you can also sort of understand what it means to different people, right? But in the earlier problems that you discussed, was a definition of hate speech or toxicity provided to the annotators, or that was also subjective?
Yeah, usually when people collect these data sets, they have like some guidance. So you could collect these annotations in a purely prescriptive way, where you have like these bullet points, like it has to satisfy each of these categories for it to be toxic. But most annotations are collected in a more descriptive manner, in that like if based on your experience or based on how you see the world, you find this offensive, you see that this might be offensive to someone else, then you can mark as a toxic. So most data sets do the latter instead of the former. But every collection process starts with some definitions. And the data sets we typically use a lot have had like higher standards of annotation than others that haven't. So that's, we use this data set by Founta, I forget their first name, but that has much higher standards of annotation. Yeah.
And you also mentioned that the agreement is quite low. That's right. So how does, let's say, machine learning algorithms compare to the agreements? So could you distinguish whether an annotation was generated by a human or from an ML algorithm?
Oh, I don't know if Oh, yeah. So could you distinguish whether an annotation came from a machine or a human? That seems very difficult to me, because you will only be seeing a label. And it really depends. Like if I give you a label and you are someone who just like is very allergic to profanities, maybe you'll think it's toxic if it contains a profanity, but maybe someone else is quite tolerant of profanities and doesn't decide it's toxic. So it's very hard to know.
Well, another way to phrase my question would be like if you consider the errors by humans, so majority vote is your ground code, and you consider errors by humans. So does the machine learning algorithm generate errors within the bounds of the human errors? Or
I think it is. It exaggerates the errors that humans make. Like sometimes, like maybe someone who is more familiar with AE will consider something in AE as non-toxic. But if there are only a few annotators even who consider AE as toxic, the model will pick up on those cues much more. At least that's what we have seen in practice, but whatever these small features are picked up.
I think Jordan is going to ask some of the online questions. Jordan,
okay.
Speak up.
Okay, we have 3 questions. I don't know if we'll get to all of them, so I'm just going to read the first one here. Are we differentiating between bias and simple errors? If so, how do you define whether a prediction is biased versus a prediction being inaccurate?
Yeah, I was kind of expecting this question. Well, so it can be both, right? So something is an error in the data because the annotator had some biases in coming to a conclusion. And there are cases where the model picks up on a bias. I mean, so there are like so many layers to this question. There is human bias, there is model bias, there's error at the level of the human, there is error at the level of the model. So yeah, I think like a better question is, you know, how can we, you know, find these better frameworks that can accommodate multiple opinions and can account for different kinds of opinions from humans? And can we come up with machine learning models? And this is probably what someone else was asking, that actually tries to capture the same uncertainty or the same kind of ambiguity that humans themselves have, instead of trying to clear cut or like clearly define what these model biases are, whether human biases are, whether some things are errors and some things are not, because nothing is 0-1 for this particular task.
Great, thanks. Bistra, do we have time for one more?
Sure, yeah, go ahead.
Okay, we got a couple more here, but I'm just going to choose one. Okay, we'll do this one. How would you detect encrypted language, i.e. language that is toxic, but acts as sort of a dog whistle and goes over the head of annotators who are unfamiliar with the group?
Yeah, oh, this is an excellent question. This is research that is currently happening at the Allen Institute for AI. And I'm really hoping that, you know, something awesome happens that can get out. This is not my own research, but it is exceedingly hard. And when we talk about annotators, even though we try very hard to hire annotators who are based in the US, not every annotator has the same cultural context. Some annotators are very plugged into politics and they know every dog whistle that happens in politics, whereas some annotators might be physically in the US, but may have come from somewhere else, and perhaps their cultural background is not the same as the dominant political current cultural background, and they might not see these dog whistles as problematic. So again, it's a very hard problem. This is the closest to this is what I've seen people do is you know, have like some documented cases of dog whistles and see if this matches in some ways. But to be honest, this is not even a problem that most humans can do pretty well. So yeah, it's an open question, but great question.
Okay, I think since we're over time, we take our speaker. Thank you very much. This is wonderful.
Thank you.